To establish an understanding of the principles of oily water separators, their operation and maintenance, we must first see why they're necessary. In the past, oil from the machinery was discharged into the sea with very little treatment. Naturally, if this continued unabated, considering the vast number of ships at sea, it would lead to intolerable conditions and to polluted beaches. Public pressure from many countries has given rise to international legislation aimed at safeguarding the seas and shores by setting standards for overboard discharge from ships. We try to maintain high standards to ensure that no oil is allowed overboard. The IMCO International Conference of 1973 on marine pollution has laid down regulations to enforce these standards. This need not happen. We who operate machinery at sea have a pride in our work, but a lack of understanding of some part of a machine or an unguarded moment can mar a normally high standard of operation. The most obvious way of preventing the discharge of oil is to prevent it ever reaching the bilge. Drip trays under machinery should be kept clean and drained when necessary into buckets rather than into the bilge. Glands should be inspected and kept sufficiently tight so that they do not leak. The purifier room should be kept clean, and when removing filter elements, they should be placed in buckets so that the oil does not drain into the bilge. But even if all reasonable precautions are taken, some oil may collect in the bilge. It is therefore necessary to separate this oil from the bilge water before discharge overboard. The basic principle of oil-water separation is the difference in specific gravity of the two liquids. If oil is poured into water and lightly mixed, the oil will float to the top, leaving clear water below. Depending on the type of oil, this separation can sometimes take place quite rapidly. But if the mixed liquids are in rapid motion, the turbulent flow in a pump or relatively small bore pipe could make separation more difficult. If the speed of the flow is reduced by, say, increasing the bore of the pipe considerably, separation starts and oil accumulates at the top. It's possible to make a good estimate of how much oil an oil-water mixture contains. This jar is a mixture of 50% oil and 50% water. This jar, on the other hand, contains only 200 parts per million of oil, and this third jar only 100 parts per million of oil. In one type of oily water separator, the oily water is led into the center of a number of concentric spiral ducts. These spiral ducts are sealed at the bottom by being welded to a circular plate, but are open at the top. The cross-sectional area of the spiral ducts is greatly in excess of that of the pipe by which the oily water enters, so the speed of the oily water is reduced to a quiet flow, and the oil starts to separate and float to the top. The object of making the ducts spiral is merely to save space. By the time the water flows out of the ends of the ducts, it is relatively, though not entirely, free of oil. Here is a diagram of how the separator works. The water, mixed with large and small globules of oil, flows rapidly down the entry pipe into the center of the spiral ducts. Here it immediately slows down, and the large globules start to separate out, rising upwards through the open tops of the spiral ducts. By the time the water has emerged from the ends of these ducts, most of the large globules have floated upwards. The spiral ducts are surrounded by a large cylinder, open at the top and bottom. The water, with small globules, and probably a few large ones, flows down the inside of this cylinder under the base of the spiral ducts. This open cylinder is enclosed in an even larger cylinder with a sealed bottom, like a very large saucepan. The water and small globules will flow under the edges of the inner cylinder and up over the lips of the outer. By now, virtually all the large globules will have floated upwards to the top of the separator, where they collect in a pool of oil in a dome. From here, the oil is drained away to a storage tank. The water, containing now only very little oil, flows down the outside of the outer cylinder to the bottom of the separator, from which it is discharged through a pipe. When the mixture, containing comparatively little oil at this stage, is flowing under the base plate of the spiral ducts, small amounts of oil will still be separating out from the water and will float up and could be trapped by the base plate of the spiral ducts. To release this oil, holes, slots or internal piping are arranged to allow such trapped oil to flow upwards. In this type of element, one of the spiral ducts is sealed at both ends, though open at the top. The base plate under this duct has holes drilled through it throughout the length of the spiral. This is such a separator. The oily water from the bilge enters here. It is pumped to the separator by this pump, which should preferably be a positive displacement type to avoid the very turbulent action of a centrifugal pump. The inlet valve to the separator can be manually operated. When the separator is in use, it should be left fully open. A partially open valve can result in turbulence. The separated oil collects at the top of the separator and flows through this valve to an oil storage tank. The valve can be closed or opened manually, but is normally operated automatically. These three probes at different levels measure the dielectric constant of the liquid in which their inner ends are immersed. This constant is different for water and oil. When the probe is immersed in water, an indicator light will be illuminated on the control panel. When in oil, another indicator light shows. Here we can see that the high-level probe is immersed in oil and the low-level probe is immersed in water. In this situation, the outlet valve will be open and the oil will be flowing into the oil storage tank. For this demonstration, we've removed the pipework so that the outflow of oil is visible. As more and more oil flows out, so the oil-water interface in the separator rises. In due course, the top probe will become immersed in water and the high-level light on the control panel will change from oil to water. When this happens, control air is admitted to the oil outlet valve, which closes. All this time, the water outlet valve is closed, so that pressure now builds up inside the separator, and this causes the water discharge valve, which is spring-loaded, to open, so that the water in the system is discharged. Oil globules continue to accumulate at the top of the separator, and the oil-water interface slowly descends. The high-level light on the control panel remains showing water. The oil outlet valve remains closed, and no flow of oil goes to the storage tank. Presently, the oil-water interface again gets down to the middle probe, and the high-level light on the control panel changes from water to oil. Control air to the oil outlet valve is now cut off, and the oil valve opens, allowing oil to flow out. The pressure in the system is relieved, so the spring-loaded water discharge valve closes. Water and oil are never discharged simultaneously. When oil is being discharged, the high-level light will be showing oil. When water is being discharged, it will be showing water. The third and lowest probe is a safety device. If a fault develops in the middle probe so that the oil outlet valve is not opened when this probe is immersed in oil, the oil-water interface will continue to descend until the third probe is immersed in oil. This will illuminate the low-level oil light on the control panel and can be arranged to trip the pump motor or sound an audible alarm. In addition to this automatic system, there are facilities for manually testing the level of oil should it become necessary to operate the system manually. This valve allows a small amount of liquid from a high level to be observed in the trough. This one tests from a lower level. The two valves are roughly equivalent to the top and bottom probes. This test valve is connected direct to the oily water inlet pipe and enables a visual estimate of its oil content to be made. Finally, this test valve is connected direct to the water discharge system and enables a similar visual check to be made. When oil flows out of the low-level valve, it means it's time to open the oil outlet valve and drain the collected oil. The opening of this valve reduces the pressure in the system and the spring-loaded water outlet valve closes automatically. This is a discharge pipe from the trough back to the bilge. There is also a system relief valve which opens automatically if excessive pressure builds up inside the separator. This also discharges into the bilge. A pressure gauge is fitted which indicates the pressure inside the separator. In very cold conditions, or when the oily water contains heavy fuel oil, both slowing operation time, it is sometimes desirable to heat the upper part of the separator to facilitate separation. An electric immersion heater is therefore fitted. This is such a separator. It is designed to reduce the amount of oil in the effluent to a maximum of 100 parts per million, as in this jar. But IMCO and other proposals require the effluent pumped overboard shall not contain more than 15 parts per million of oil, as in this second jar. It is therefore necessary to have a second stage which reduces the oil content still further. This is done by means of a coalescer. The buoyancy of a globule of oil in water depends on the volume of the globule, but the speed of rising depends not only on the difference in specific gravity of the two liquids, but on the friction on the surface of the globule as it moves through the water. With a minute droplet of oil, the skin friction may be sufficient to prevent it rising at all. But a globule of twice the radius will have 8 times the volume, but only 4 times the surface area. It will therefore have a far greater tendency to rise. If we join up or coalesce 8 small globules into one large one, the increase in volume will be greater than the increase in surface area. Therefore, the increase in buoyancy will greatly exceed the increase in skin friction, and so the resulting large globule is more likely to rise. This is the principle of coalescence. Externally, the coalescer is rather similar to the separator, but internally its construction is quite different. In this type of coalescer, the oily water is fed into the bottom center of an element by means of a perforated pipe. The top and bottom of the element are sealed so that the oily water can only escape radially through the coalescer element. It first has to pass through a crimped screen of needle felt. This does not impede either the oil or the water, but collects any particles of solid matter that may be suspended in the mixture. The oily water then has to pass through a series of glass fiber concentric cylinders with perforated formers between them. Water passes easily through these, but oil is to some extent impeded. Small globules of oil stick to the glass fiber and in time coalesce with others, forming larger globules. In due course, pressure from the inside forces these larger globules right through the cylinders to the outside, where they rise rapidly. Outside the coalescer elements, and there may be a number of them, depending on the required throughput of oily water, is a fine mesh stripper made of nylon. The design flow is such that oil globules will bounce off this and continue their upward path, while the water will pass through. The oil globules collect in the dome at the top of the coalescer, and the oil then flows into a holding tank, joining the oil from the separator. The water flows down to the bottom of the coalescer, by which time its oil content will not exceed 15 parts per million. It may then be discharged overboard. The oily water in the separator is piped to the coalescer through an isolating valve. This valve is worked manually and is left full open when the equipment is in use. On entering the coalescer, the liquid slows down and passes through the coalescer elements, as we've seen. The oil collects in the top dome in a similar manner to the separator. On the coalescer, however, there are only 2 probes. The upper probe initiates a signal which opens and closes the oil outlet valve. It is closed when the probe is immersed in water and a water indicator light is illuminated on the control panel. Clearly, if the upper probe is immersed in water, so will be the lower probe, and its water indicator light will show on the control panel. In this condition, the outlet valve is closed, so no oil flows to the storage tank. Since there is so much less oil in the liquid compared with that in the separator, the level of the oil-water interface falls very slowly, so that 2 separate operating probes are not necessary. When the upper probe is completely covered with oil, an oil indicator light is illuminated on the control panel for the high-level probe, and the oil outlet valve opens and allows oil to be drained to the storage tank. There is a spring-loaded water discharge valve, which closes automatically when the pressure inside the coalescer is relieved by opening the oil outlet valve. As with the separator, oil and water are never discharged simultaneously. The lower probe is a safety device in case the upper probe fails, or in case the oil outlet valve remains closed. In such circumstances, the oil-water interface will continue to descend until oil covers the lower probe. When this happens, the light for the low level on the control panel will change from water to oil and can be arranged to trip the pump motor or sound an audible alarm. As with the separator, there are manual test valves. In this case, the high-level test valve is connected to the extreme top of the equipment. This is useful when servicing the equipment. Two pressure gauges are fitted, one reading pressure before and one after the coalescing elements. The first should read only slightly lower than the pressure in the separator, allowing for frictional losses in the intervening valves and pipework. There is a spring-loaded relief valve which opens to the bilge if excessive pressure builds up inside the coalescer. Finally, there is an electric immersion heater for excessively cold conditions or for use with heavy fuel oil. First, at regular intervals, generally about once a month, it is advisable to clean both stage 1 separator and stage 2 coalescer. Ensure that all oil has been drained from the oil recovery domes and that the system is full of clean water, either seawater or fresh. If it is not convenient to pump clean water through the normal mixture inlet valve of stage 1, a filling line may be used to a separate initial filling valve. When the system is full of clean water, switch on the electric heaters. The filling valve is now closed and the contents of the whole system are allowed to become hot. When the system is hot, clean water is pumped through it by once more opening the initial filling valve. Occasionally, the manual oil outlet valves are opened on both stage 1 and stage 2 to drain any oil. Now, while continuing to pump clean water through the system, the drain valves on both stage 1 and stage 2 are opened. Pumping of clean water through the system is continued for a short while. After this, the two drain valves are closed again. The filling valve can now be closed and the system left full of clean water. This prevents internal turbulence when restarting the plant and reduces corrosion when the plant is idle. Infrequently, probably about once a year, the coalescer elements will require replacing. As much oil as possible is evacuated from the coalescer. Use the high-level test valve, since this is connected to the extreme top of the dome. When the whole system has been cleaned internally and is full of clean water, the mixture inlet valve on stage 1 is closed. Then the isolating valve on stage 2 is also closed, and also the shipside valve. The stage 2 drain valve is now opened and the coalescer is drained. We now prepare to remove the coalescer dome. The wiring and pipe connections to the top cover are disconnected. The top flange of the coalescer may now be unbolted. The dome can then be removed, which gives access to the coalescer elements. Finally, the coalescer elements can be removed by taking off the securing nut and element cap. When all the dirty elements have been removed, new elements may be fitted and the coalescer reassembled. Make sure that the correct coalescer elements are fitted as recommended by the manufacturer. Be careful not to omit this washer, since if you do, the element will not be properly sealed. It is very important when reassembling to see that the faces are clean and correctly jointed so that there are no leaks after completing the reassembly. All such equipment must have a certificate of approval which must be prominently displayed. Study the operating manual for your particular equipment. Correctly operating your equipment will be another step in keeping the seas clean and the beaches free from pollution.